Hello students, welcome to RSA Online. In this session, we'll be dealing with Module 5 of Cryptography and Cybersecurity from Semester 8 of Information Technology branch. Myself, Nikhila from Rajagiri School of Engineering and Technology. In this session, we'll be dealing with public key cryptosystems. What is a public key cryptosystem? What is the difference between a public key cryptosystem and a private key cryptosystems? And a well-known algorithm, RSA algorithm, is also discussed in this session. The key generation, encryption and decryption in RSA is also discussed, and what are the security issues related with RSA are the things that are dealt in this session. In the previous module, we have already seen private key cryptosystem. Difference between the private key cryptosystem and the public key cryptosystem is that the private key cryptosystem involves only a single key, whereas in the case of a public key cryptosystem, there will be two keys. One key is called as a public key, another one is called as a private key. The public key is used for encrypting the messages and the private key is used for decrypting the messages. It is also called as asymmetric encryption, as it involves two keys. And this asymmetric cryptosystem or the public key cryptosystem is implemented or has been introduced only to complement the private key cryptosystem, not to replace the private key cryptosystem. A public key encryption scheme has 6 ingredients: a plain text, an encryption algorithm, a public and private key combination, cipher text, and the decryption algorithm. The essential steps are the following. Each user generates a pair of keys to be used for encryption and decryption of the message. Each user places one of the two keys in a public register or other accessible files. This is the public key. Here you can see Bob's public key ring. If Bob wishes to send a confidential message to Alice, Bob encrypts a message using Alice's public key. When Alice receives the message, she decrypts it using her private key. No other recipient can decrypt the message because Alice knows Alice's private key. Because only Alice knows Alice's private key. This is how the public key crypto system can be used for ensuring confidentiality. The same way, public key crypto system can be used to ensure authenticity of the messages too. To ensure the authenticity of the message, then the message should be encrypted using the sender's private key, because only the sender will be having its own private key. So once a message is being encrypted using the sender's private key, it ensures that it is that particular person who has done the encryption, and the decryption will be done using the sender's public key. The first and foremost application of public key crypto system is encryption and decryption. Is to ensure the confidentiality, and there are two more issues that could be solved using, or that could be addressed using public key cryptography. The first issue is key distribution or key exchange. There's two sides. That is, the public key cryptography can be used to exchange the secret keys which is used to encrypt the messages. Two sides cooperating to exchange a session key, which is a secret key for symmetric encryption, generated for use for a particular transaction and valid for a short period of time. And the second issue that is being addressed is digital signature. The sender signs a message with its private key. Signing is achieved by a cryptographic algorithm applied to the message or to a small block of data that is function of the message. This block diagram helps us to explain how public key crypto system can be used to ensure the confidentiality as well as authenticity of the message. Here there is a message source over here which generates a message that is depicted as X in the figure, and initially this X is being encrypted using the private key, that is the key KRA is called as the private key of A. That is, only A will be having its private key. So it once you are encrypting the message using the private key of A, then it ensures the authenticity of the message. That is, the message is being encrypted only by A is what here it can assure you. And then this encrypted message which is depicted as Y is again encrypted using the public key of B, that is KUB is the public key of B, and once it is being encrypted again using the public key of B, that ensures the confidentiality of the message. That is, this message could only be decrypted by B's private key. Nobody other than B can decrypt the message. So that ensures a confidentiality. At the receiving side, the private key of B is used to decrypt the message first, and then the public key of A is used to decrypt the decrypted message. And then you get the message X from the crypto system. Here we are trying to explain what is a one-way function and what is a trapdoor one-way function. A one-way function is a one that maps a domain into a range such that every function value has a unique inverse with the condition that the calculation of the function is easy, whereas the calculation of the inverse is infeasible. That is, y is equal to f of x is easy and x is equal to f inverse y is infeasible. A trapdoor one-way function which is easy to calculate in one direction and infeasible to calculate in the other direction unless certain additional information is known. With the additional information, the inverse can be calculated in a polynomial type. A trapdoor one-way function is a family of invertible functions such that some additional informations are known. Here we are going to describe one of the famous public key encryption algorithm, RSA. RSA is an abbreviation of three mathematicians by the name Rivers, Shamir, and Edelman. RSA scheme is a cipher in which the plain text and the cipher text are integers between 0 and n minus 1 for some n. A typical size of n is 1024 bits. Here we are trying to explain the different steps involved in the key generation of RSA. As we have already seen that RSA is a public key encryption algorithm, and in any public key encryption algorithm there will be two keys, a public key and a private key. So to generate the public and private key encryption algorithm, the steps to be followed are: initially we have to select two large prime numbers. Let it be named as P and Q. Then we find the product of P and Q and name it as N. After that, we are supposed to calculate phi of n, which is called as the Euler-Stoichhian function. We have already seen how to compute Euler-Stoichhian function, and as n is a product of two prime numbers, then the Euler-Stoichhian function of m could be written as p minus 1 into q minus 1. Now we are trying to find out the encryption key, which is marked as E. So So always E should lie between 1 and phi of n in such a way that GCD of E, comma phi of n should be equal to 1. Now we're trying to find out the decryption key D. Decryption key D should be the multiplicative inverse of E. That is, E multiplied with D should be congruent to 1 mod phi of n, and D should lie between 0 and capital N. Now we publicize the public key, that is a combination E, comma N, and keep the private key as a secret key. That the private key combination is D, comma P, comma Q. The encryption-decryption procedure of RSA is what's depicted in the figure. As we have seen in our previous slide, our encryption key is E and N, and our decryption key is D, P, and Q. Here Alice needs to send a message to Bob, and after the calculation of the private public key combination, Bob has publicized its public key combination E, comma N, and Alice will be using E, that is a public key of Bob, to encrypt the message. RSA encryption algorithm uses the concept of modular exponentiation, and the ciphertext C is being computed using the equation P raised to E mod N. And at the receiving side, the plain text is being received from the ciphertext using C raised to D mod N. RSA encryption algorithm uses two algebraic structure. For encryption decryption, it uses the commutative ring, and for the key generation, it uses the groups. This group, which is defined on Z of phi of n star on the operation multiplication. Here we have got the algorithm for the RSA key generation. The detailed step we have already discussed in the previous slide. Here we have got a problem for RSA, that is, we initially selected two prime numbers 17 and 11, and using these two prime numbers 17 and 11 we found out n, which is a product of p and q, and from that we can find out phi of n, which is the Euler's torsion function, that is 17 minus 1 into 11 minus 1, that is 16 into 10, which is 160. So phi of n is 160, and now we are trying to find out e such a way that GCD of E, comma 160 should be 1. That is, E and 160 should be relatively prime to each other. So, E could be taken as 7. 7 and 160 are relatively prime to each other. Now, using this E, we are trying to find out the decryption key D. And to find out decryption key, the D will be the multiplicative inverse of E under the modulus of phi of n, under the modulus of 160. So, D could be find out as 23. Now we publicize our public key, that is, public key will be always a combination of E and N. So E is 7 and N is 187, and the private key will be the combination of D, P and Q. So D is 23, P and Q are 17 and 11 respectively. Using the generated RSA keys, we are trying to encrypt the message and decrypt the same. The given message is 88. To encrypt the message, the ciphertext is formed as m raised to e mod n. Here the value of e is 7, so we have to do 88 raised to 7 mod 187, which is equivalent to 11. And on the decryption side, what we have to do is we have to use our private key. Our private key is 23. So what we have to perform 11 raised to 23 under the modulus of 187, which is equivalent to 88. different attacks which are possible on RSA are brute force attack, mathematical attack, timing attacks, hardware fault-based attack, and chosen ciphertext attack. In brute force attack, as we already know, we try out all the possible private keys to find out the plain text. The next main attack which is possible on the RSA crypto system is a factorization problem. It's a mathematical attack. We can identify three approaches to attack RSA mathematically. Factor n into its prime factors. That is, as we all know, n and e are made public. This enables to calculate phi of n, which is a combination of p minus 1 into q minus 1, which in turn enables the determination of d, which is congruent to E inverse mod phi of n. And the second one is determining phi of n directly without first determining p and q. Again, this enables determination of d, which is congruent to E inverse of mod phi of n. And the third one is determining d directly without determining phi of n. A timing attack is somewhat analogous to a thief guessing the combination of a safe by observing how long it takes for someone to turn the dial from number to number. Here, the operation that is being exploited is the exponentiation operation. The attacker tries to compute the time taken for exponentiation. The countermeasures to avoid this timing attack are the constant exponentiation time, inserting a random delay, and blinding. In constant exponentiation time ensures that all exponentiation takes the same amount of time before returning a result. In random delay, better performance could be achieved by adding a random delay to the exponentiation algorithm to confuse the timing attacker. Blinding, multiply the ciphertext by a random number before performing exponentiation. The approach is an attack on the processor that is generating RSA digital signature. The attack induces fault in the signature computation by reducing the power to the processor. The fault causes the software to produce invalid signature, which can then be analyzed by the attacker to receive the private key. This attack, while worthy of consideration, does not appear to be a serious threat to RSA. It requires that the attacker have a physical access to the target machine and that the attacker is able to directly control the input power to the processor. Chosen ciphertext attack, which is also known as CCA, is defined as an attack on which adversary chooses a number of ciphertexts and is then given the corresponding plaintext decrypted with target's private key. Thus, the adversary could select a plaintext, encrypt it with the target's public key, and then be able to get the plaintext back by having it decrypted with the private key. Clearly, this provides the adversary with no new information. Instead, the adversary exploits properties of RSA and selects blocks of data that, when processed using target's private key, yield information needed for cryptanalysis. To counter such attacks, modifying the plain text using a procedure known as optimal asymmetric encryption padding (OAEP) is being recommended. Here we have discussed what is a public key cryptography or crypto system, and we have discussed an example for the public key crypto system, that is an RSA algorithm, the key generation of RSA algorithm, how is encryption and decryption done in RSA algorithm, and some problems related to the same.